Our stormwater program, we stormwater solar farm projects often come under our construction stormwater permit, and we have tools and guidance, calculator to help permittees with that. I saw Dr. Mulla and Brian speak at a recent conference and was intrigued by the information they provided and thought that maybe the tools and resources that we have could be updated based on the research information that was presented in those talks and our desire to promote both solar farm development and the use of green infrastructure and native vegetation. So I asked them to come in and speak, and they cordially agreed. I'm going to introduce both Brian and David together, and then they can pass it on um, amongst themselves during the presentation. So Brian Ross is a vice president at the Great Plains Institute, leading renewable energy market transformation efforts in the Midwest and nationally. Over his career, he has worked with over 100 local, regional, and state governments on sustainable development, including natural resource planning, transportation planning, and climate and clean energy planning policy and regulation. Brian currently leads multiple efforts to develop model ordinance and best practices for integrating solar development with natural systems, community priorities, and agriculture business models. As part of the National PV Smart program, he developed solar project post-construction water quality guidance and best practices for water regulators and for solar developers based on groundbreaking field research and modeling. Dr. David Mulla is the Larson Chair and Professor for Soil and Water Resources in the Department of Soil, Water, and Climate at the University of Minnesota. Dr. Mulla received a PhD in agronomy from Purdue University with emphasis in soil physics. He was a soil physicist and professor in the Department of Crop and Soil Sciences from 1983 to 95 at Washington State University. Since 1995, he has been professor and Larson Chair for Solar and Water Resources in the Department of Solar, Water, and Climate at the University of Minnesota. In 2004, he was appointed director of the Precision Agriculture Center at the University of Minnesota. Dr. Mulla's research emphasizes precision agriculture and precision conservation, land management and water quality interactions, ecosystem services, and international agricultural development. He also studies non-point hydrology and water quality measurement and modeling. So Brian, I believe you're up first, so I'll pass it on to you, and thanks again for coming in to present.
All right, thanks, Mike. We'll go ahead and get started here. As you can see from the start of the presentation screen there, that we are talking about the PV Smart project today, the photovoltaic stormwater management research and testing. It is a DOE, Department of Energy funded program, 3-year program that is being led by the National Renewable Energy Lab, whose Golden, Colorado campus you can see here with all its pervious pavers and net zero energy building is what they're hoping to get to. Other partners in the project, including Great Plains Institute, who I represent, we're a nonprofit organization based here in Minneapolis, working nationally on decarbonizing our energy system, is the University of Minnesota, doing all of the field research and the modeling. Fresh Energy was a partner who is working mainly in communications, and then of course the National Renewable Energy Lab is the lead entity. The issue why this came up is really about how the burgeoning market in solar energy is being treated in a variety of different circumstances, including in the permitting world, the stormwater permitting and water quality integration with water quality programs. We have a very rapidly growing market. At the end of 2020, the Lawrence Berkeley National Lab, which tracks this, reported that there was only over 676 gigawatts of large-scale solar projects in the interconnection queue, which is where projects have to go in order to interconnect to the grid. They have to provide an application and demonstrate that they have secured the land over which their project is going to move ahead. And that 676 is not gigawatts, may not mean much, but in context, it's over 10 times the current deployment of large-scale solar in our nation, which is about at 62 gigawatts. So this is just what the market is delivering to us right now in terms of people who have projects that want to move ahead and think they have buyers. This is how the market is moving. If developed, this would be about 5.4 million acres of land, primarily in rural watersheds, because these are large-scale projects. Now, the caveat is that most of these projects actually will not be developed for a variety of reasons. They will fall by the wayside, but it is an indication of the market and an indication of where the market is going over the next 10 years. As a result of that, what we were seeing is a lot of jurisdictions that were treating ground-mounted PV facilities in a variety of different ways, including some that were looking at it primarily as impervious surfaces, especially at the local level, and in some of the, not only the construction stormwater permitting, but other kinds of water quality permitting. And we looked at the models being used by local and state jurisdictions and really discovered that almost none of them were tailored to solar development. In fact, Minnesota was kind of unique in the nation of having made an effort to actually tailor the calculations of stormwater runoff to the kind of solar development and land use that was in place. But almost everybody was relying on non-solar research or findings in order to kind of do their estimates. The ultimate thing that occurred from this is that it led to higher costs and slower deployment of solar, and frequently even to suboptimal water quality outcomes. And so the DOE funded this program in order to address those kinds of things. And so we're kind of going out now and we're nearing the end of the project. We're looking at Minnesota in terms of the market here as similar to the national market. We have about 3,200 megawatts of proposed projects in Minnesota right now, solar, which is almost doubling the amount of solar that's currently installed in the state. And we are expecting by 2030 to see something like 6 to 10 gigawatts of solar installed in Minnesota, which of course is several times what the current installation is. So we're going to see a growing market here and a growing need to address how we integrate solar with water quality and other kinds of local impacts for the host community, including kind of the idea of how do we develop co-benefits for those communities. So this project was really looking at reducing that balance of system soft costs, as we call it, which is the permitting cost for solar development, especially as it's related to, in this case, stormwater infrastructure requirements, but also to improve water quality outcomes if we could do that by developing and disseminating these solar-specific resources for estimating solar runoff, stormwater runoff, sorry, and to develop best practices for stormwater management and water quality. The project, which started about 2.5 years ago, had as its core to first establish and engage a national water quality task force of people made up of a variety of different perspectives on water quality and solar, to conduct field research on stormwater infiltration and runoff at 5 ground-mounted sites in 5 different states across the country. And Dr. Mulla will explain kind of how those differ and what we went for in terms of the kind of variety of those. Using that field research to conduct hydrologic modeling and generate stormwater runoff coefficients for a variety of site conditions, to develop stormwater best practices and water quality best practices for both regulators and for solar projects that would hopefully both make a transparent and predictable process for the developers and improve water quality outcomes for the regulators and for the communities that are hosting these sites. And to engage with local jurisdictions and other stakeholders once we develop these things to disseminate the best practices in stormwater runoff coefficients. Our National Water Quality Task Force, I have listed here, it does include several Minnesota connections, but also includes, for instance, a couple of folks from the National EPA who have been working in water quality for some time. It includes solar EPC contractors, solar developers, native, or I should say, landscape architects and designers working both in the solar world and outside the solar world representatives from local governments, state regulators, and academics. So we try to catch a wide variety of folks who have been giving us advice and giving us feedback on these processes as we've moved forward over time. We do have a project website where we will be publishing everything. We have, you can currently go here to get some examples of studies that have been relevant to the project, as well as some of the work that we've already published in the, for instance, the interim best practices that we developed after the first round of analysis and modeling. So that's kind of the background of the story and the study. If you have any questions, I'm happy to answer them on that, but otherwise I will hand it off to Dr. Mulla to discuss the details of the modeling and really get into the nitty-gritty of kind of what we found. So I'll just pause here, and if there's any questions, otherwise, David, why don't you go ahead and take it over?
All right, thank you very much, Brian. Can you see my screen?
Yes. You're not in presentation mode, but there you go. Now it is.
All right. So my co-author is Jake Galsky, who did a lot of the modeling. And as Brian said, our objective is really to develop some best practices for reducing stormwater runoff and to use experimental data from 5 sites across the country to develop a runoff calculator that takes into account things like panel spacing, precipitation, soil and topography, and different kinds of vegetative cover. And here's a brief sort of introduction to the sites we're studying. We have sites in New York, Georgia, Minnesota, Oregon, and Colorado. And they have a variety of different vegetation, different soils, different climates. Some of the arrays are fixed, others are tracking. And so this little slide here shows some of the differences. We have soils that are well drained in Minnesota and soils that are really poorly drained in New York and Oregon and Colorado. New York and Georgia are wet, Oregon and Colorado are dry, Minnesota is kind of in between. So at each site, we're trying to capture the 3-dimensional nature of the hydrology, which is a combination of precipitation intercepted by impervious panels, which then drips off and creates a lot of concentrated flow right at the drip edge. You also have precipitation in the middle of the arrays. And then water can infiltrate or run off and be taken up by the plants and transpired. So at our sites, we're measuring precipitation on site. We're also measuring how much of the precipitation runs off of the edge at the fixed array sites. And then we're installing moisture probes under the panel, under the drip edge, and between the arrays, generally at 2 depths. We're characterizing the sites for topography, soils, vegetation, climate, and then we're taking measurements of soil moisture and infiltration and runoff. We use a numerical model to evaluate the ability to represent the experimental data. This model is a numerical model that allows for consideration of 2- or 3-dimensional water flow using the Richards equation. And the inputs include soil characteristics, saturated moisture content, saturated hydraulic conductivity, we set the model up so that the initial antecedent moisture content is the field capacity. We could set it to any other thing we want. We could set it to saturation if we wanted. But most of our sites before storms would be at field capacity. And then we actually measure, the precipitation running off the drip edge. And generally speaking, we're setting it to a value of about 10 times the precipitation. But we have seen lower amounts as well at some sites. We are using design storms for a 24-hour period. And I'll talk about that more in a minute. And the lower boundary condition of our simulation is no flux, no drainage. So it's kind of a worst case scenario. And the soil depth varies depending on the site-specific soils that we have in place. Inside the model, we have to know the relation between soil moisture and soil matrix potential. And so there's an equation we use called the Van Ganuten equation. It has two parameters, alpha and n, which we have to fit based on experimental data. That same equation can be used to predict the saturated and the unsaturated hydraulic conductivity, which varies with matrix potential. And so these are all time dependent. So here's some data for the model calibration, showing that it actually is very, very accurate over a long period of time. You can see for the sandy clay soil at one of our sites, the green line is the measured data, and the red line is the model data, and the blue vertical bars are the precipitation events. So we calibrate for the hydraulic conductivity, and we don't change it too much from what we actually measure, but there's some slight change. And as you can see, our root mean square error is very low for all the sites that we have. Now, the advantage of this model is we can look at the disconnected pervious nature of ground-mounted PV sites. So you have pervious soil between the arrays and impervious arrays, which intercept the runoff, but underneath the arrays, it's actually impervious. It's actually pervious. So the runoff can go down slope and then infiltrate underneath, a downslope array. It's not impervious underneath the array. And the model can handle the concentrated panel runoff, the incident precipitation in the area between the arrays, the routing of runoff and infiltration underneath the next panel, and then the total accumulated surface runoff from the entire system. And, simulating infiltration and runoff for different types of soils shows pretty big differences between sandy soils and heavier textured soils, as you might expect. So for a 24-hour, 100-year storm on sandy soil, there's actually a lot of infiltration beneath the drip edge and not too much runoff. Whereas with the silty clay loam soil, which is, has less infiltration, you get more runoff and wetter soils. So we're using design storms for this modeling. We have 2-year, 10-year, and 100-year return frequencies, which are based on Atlas 14 data for the individual states where our sites are located. And so this graph just shows the differences in the depth of the design storms for the different locations. You can see, the range is from about 5 centimeters to about 25 centimeters. So that's, anywhere from about 1.5 inches to maybe 10 inches of rain in 24-hour period. So the first result I'm showing here is sort of our baseline condition for each of the sites, for each of the design storms. And in Minnesota, for example, very, very sandy soil, there was no runoff whatsoever, even at the 100-year design storm. On the other hand, at New York, we had runoff at every design storm, and the same was true at Oregon. At Georgia and Colorado, runoff only occurred when we had the 100-year design storm. For New York and Oregon, the runoff increases on average by about 160% for the 100-year versus the 2-year design storm. So that's a big change. Next, we looked at the effect of soil bulk density. Bulk density can be affected by pre- and post-construction management and maintenance factors, like heavy equipment driving on the soil, mowing, ripping or scarifying the soil, etc. So generally, higher bulk density would be compacted soils, and lower bulk density would be loose soils. You can see here that runoff is highly sensitive to bulk density. So the baseline is the blue bars, which have a kind of normal bulk density. And if we increase bulk density, runoff goes up. If we decrease bulk density, runoff goes down. We looked also at where the bulk density was being changed. So the sort of red or orange bars are compaction under the panel or in the full sun area, and the greener ones are, decreasing bulk density by ripping or scarifying the surface in the full sun or right at the drip edge. And so you can see there's differences for all of these factors. But on average, if you have compacted soil, which is the worst case scenario here, versus uncompacted soil, which is the best case scenario, that is a difference of about 100% in runoff averaged over these 5 sites. Next, we looked at the effect of soil depth. And obviously, in our experimental sites, we had some soils that were 50 centimeters deep. I think that was New York. And we had some soils that were 150 centimeters deep. I think that was Georgia. And so the runoff changes as you get deeper soils. On average, the deeper soils about 80% less runoff than the shallower soils. Next, we looked at the effect of array spacing. All of the study sites we were at had 25-foot on-center panel spacings, but we changed, in the simulation, the spacings to 15, which is to maximize the capacity to generate solar power, relative to 35-foot spacing, which maximizes the amount of pervious surface to infiltrate runoff. And here you can see that increasing the spacing decreases the runoff, and on average there's a increase of 14% in runoff as the panel spacing decreases from 35 to 15 feet. Next, we looked at the effect of vegetation. So a range from row crop to mature prairie, or in between that, we have a kind of newly established pollinator habitat. And Row crop always generated more runoff than the restored prairie or the very mature vegetation, deep-rooted vegetation. And runoff increases on average by 38% for row crops relative to mature pollinator or restored prairie. Next, we looked at effective vegetation with and without arrays. So you're looking at like what the change would be from a baseline that had a certain type of vegetation to the situation where you have ground mounted PV panels at a 25-foot spacing with the same vegetation. The blue bars are the 100-year design storm depth of precipitation, and the green bars would be the runoff without arrays. The red bars are the runoff with arrays. On average, switching to the system with arrays increased the runoff by about 14%. And then just to kind of put this all in perspective, we compared runoff for our 5 sites with a 100-year 24-hour storm using our hydrous runoff predictions relative to the NRCS runoff curve number for the same type of vegetation. And you can see that on average, the hydrous model gives less runoff than the runoff curve number method. However, at New York, which is the site where we had very shallow soil, our model predicted more runoff than the runoff curve number method. But on average, across all the sites, the hydrous method had 38% less runoff than the NRCS runoff curve number method. And this is really significant for developers and when you're considering whether or not to give a permit to a developer, because it tells you that, you know, the disconnected nature of the impervious surfaces is fairly effective at infiltrating runoff. And that means that if your methodology was to assume that the site was totally impervious, which a lot of states are using, you would over-predict the runoff by a vast amount. And, you know, that would mean developers have to spend a lot of money to install stormwater detention practices. So to kind of conclude on this modeling part, the hydrous model was accurately able to estimate runoff for our sites. And we looked at a range of different factors and their relative impact on runoff. And these are ranked in terms of their decreasing importance. So design storm depth is the most important. Soil compaction is second. Soil depth is third. Type of vegetation is fourth. And then the difference between having arrays or no arrays is pretty low. And panel spacing is also fairly low. And again, on average, our method generates less runoff than with the NRCS curve number. Now I have a couple of more slides which I'm going to talk about to show how we put all this together into a runoff calculator, but I thought I'd stop for just a minute and see if there's any questions on the hydrous modeling at our 5 experimental sites. And I'm not really able to see the
looks like Mike is raising his hand. I don't see any questions in the chat, but it looks like Mike might have a question.
Mike, go ahead.
David, I had a question about the vegetation. Are you seeing differences in the effects of vegetation with soil? For example, is perennial vegetation better or worse at reducing runoff at sandy soils versus clay soils, for example?
Yes, there's an interaction between the vegetation and the soil. Um, and so that is accounted for, in our model. It comes about through differences in evapotranspiration, which, changes antecedent moisture content. And it happens also through, changes in bulk density. So we actually measured bulk density at all of our sites, and that's, strongly affected by the density of vegetation and the rooting depth. All right, there were a few things in the chat I saw. So Joe asked, was there any monitoring to calibrate or verify the model? And yes, I covered that early on. We did calibrate and validate the model at all 5 sites, and I showed a slide with root mean square errors, which were, around 0.02, so pretty low, and pretty high R squared values. Second question was, how is soil depth defined? We're using the Surgo map units to define soil depth, and so generally that's the depth of the rooting zone, or the depth of the A, B, and C horizons in the soil. So not necessarily to bedrock, but many times, yes, that would be below the sea horizon, there would be bedrock. Okay, I don't see any other questions right now. So I'll proceed to the last couple of slides, which I think would be of great interest. So this is about generalizing the hydrous runoff modeling to handle a wider range of conditions than we actually studied experimentally. So we estimated runoff for a wide range of soil textures as shown on this soil texture triangle. We also simulated different soil depths and bulk densities for 2, 10, and 100-year design storms with antecedent soil moisture of field capacity. And then we used the NRCS runoff curve number model, which is given in yellow here, to actually fit our data across the different design storms. So we took a particular soil texture and then did the regression with this model. And the factors in the model were the bulk density and the soil profile depth. And we did that for every soil, and then generate a lookup table that could be used to quickly calculate the runoff curve number and the amount of runoff. So it's basically not feasible for the average user to run a complicated model like this on every site, although if they wanted to, they could. We've sort of outlined how that's done. To generate this sort of runoff calculator, we ran hydrous about 1,000 times for different soil textures, soil depths, soil bulk densities, and design storms. And then we used the regression models in the calculator to basically allow the user to input their soil texture, soil profile depth, bulk density, the type of vegetation, whether or not soil patterns or panels are present, panel spacing, and then percent slope. And so the blue cells here are the inputs, and the orange cells are the outputs. So in this particular example, for silty clay with a shallow depth, a really kind of normal bulk density with a newly established pollinator in the presence of 25-foot spacing solar arrays on a 5% slope. The runoff curve number for antecedent moisture content of field capacity is about 45. And if the antecedent moisture content is saturated, then it goes up to about 65. And then you can enter a 24-hour precipitation event. And here I did 3 inches. And that generates very little runoff for the antecedent moisture content that has field capacity, but it generates about a half an inch of runoff when you have your saturated soil as antecedent moisture. On the other hand, for a loamy sand with the same other factors, so just changing the texture, you see that the runoff curve number goes down to 30, and there's no runoff generated for a 3-inch storm. If the antecedent moisture content is saturated, then it goes, the runoff curve number goes up to 50, and the runoff increases slightly, but still rather minimal. So the bottom line here is this is very quick and easy to use. We anticipate that, it would be a big step forward for a lot of agencies, both at the state, federal, and even local levels, to use a tool like this. And the runoff curve numbers could be taken out of this model if wanted to do that, and put into a more sophisticated model like SWIM, if the user had the capability to run SWIM or something like that, and they could use the runoff curve number from this calculator to do more sophisticated simulations for, entire site. So to conclude, we developed this user-friendly runoff curve number calculator. It handles different soil textures, soil depths, soil bulk densities, vegetative covers, presence or absence of solar arrays, panel spacing if you have arrays, slope, and you just entered the numbers and it immediately gives you a result. There's no waiting time. It's instantaneous. And then if you're interested, you can put in a design storm and estimate the actual depth of runoff, and then use any method you have for calculating what amount of runoff needs to be mitigated based on your local regulations. So that is basically the presentation I have for today, and I'm willing to take questions on this latter part as well. I think there are some questions in the chat already. So let me go into the chat. All right. So Mike had asked, okay, I'm going way back here.
I think if you go up to Fox, that was the last question in the chat that I do not believe was answered.
Yeah, Fox had asked if there's any inclination as to whether these findings would hold for larger rain events. I think they would hold. We do plan to run some larger storms just to see whether that's true or not. So thanks for that suggestion. I know Jake answered one of the previous questions about calibration and validation. So that's in the chat. Mike asked, is there guidance about recommended vegetation at sites, considering areas under panels are shaded? And yes, we did notice that there were areas under the panels, especially in the more arid sites, that had less vegetation. So it would be interesting. I think if you go to Dan Shaw's information at Bowser, he does have guidance about seed selection and, pollinator mixes that might do better in shaded conditions or dry conditions. So that is a concern, but the good part of this is that the area between the arrays is still generally well vegetated at all of our sites. And so that area is pretty effective at generating infiltration. Go to another question here. Could you incorporate grazing as a cover type? We actually have 2 sites where we can sort of evaluate those effects. We haven't done so yet. In New York, they actually are grazing sheep, and we have monitoring equipment in both the grazed and the ungrazed sites. Right now, our model is only calibrated for the ungrazed site, but we will be looking into the grazing part later. In Georgia, they're kind of simulating grazing by mowing the vegetation rather regularly. So again, that's something we might be able to handle. Another question, in generalizing the model, is it relevant to account for vegetation cover with fire? That's something we haven't had asked before. I think it would be a disaster, actually, if there was a fire at some of these sites. We did have one of our sites in Oregon, which was right in the middle of a big area of forest fires. We came very near to actually having a fire at our site. The day that Jake was out collecting field data, the air quality was off the charts. I mean, it was an AQI of about 200 because of the smoke. So we did come close to that, but hopefully it's not something we have to account for in our model. And then Mike asked, is the model available now? And is it in public domain? It's not available yet. We're still making some final tweaks, but we expect it will be in the public domain by the end of the year and will be available for the public. So that's really great to hear all these questions. We've been getting a lot of interest from all over the country in this project. And we think that there will be a lot of people trying to use this tool because aside from Minnesota, there really aren't any states that have calculators that can be used for this purpose. So thanks for all the questions. I'll turn it back over to Brian. I think he has a few wrap up slides.
Yeah, thanks, David. That was great. And just to get some of the questions related to some information that we had been generating, in addition to the modeling, we had been doing a lot of discussion and interviews with both regulators in different states, as well as solar developers and contractors who are doing ground cover and stormwater management on behalf of the solar industry, as well as some water quality organizations like Center for Watershed Protection that is just generally concerned with this. So, some of we heard a lot of feedback on some of the questions on, for instance, that Mike asked on vegetation, how you ensure vegetation under the panels versus in the full sun area, what kind of how important that is, what are the processes and techniques to do that, as well as a number of questions that relate to some of the findings that David had presented on things like compaction. What is the best methods to mitigate for or avoid in the first place compaction in the construction process? And we've been trying to kind of get a sampling of that. It was we heard a diversity of opinion around it, but generally that there was some evolving, on the relationship to Mike's question, some evolving practices and seed mixes for what you do under the panels versus in the full sun area, as well as the impact of panel height on the ability to get to a vegetation density that would both provide co-benefits as well in terms of habitat, as well as better infiltration opportunities underneath the panels. So those are not maybe scientifically validated, but we did get a sampling of that, of some of the best practices that people are trying to use to address that. And I'll just kind of in the last few minutes here, let's see, get my. Okay, people can see that, hopefully. We did, earlier in the project, about halfway through, since we were getting a lot of calls for when we were going to have some results on this, we developed a set of first we did an assessment of existing practices in the regulatory realm, looking primarily at state regulation, but also to some extent at what different local governments were doing in terms of their administration of construction stormwater or other kinds of permits, water quality permits that were relevant to the development. And we developed a kind of a document that kind of outlined some of the barriers in existing practices that we saw to solar development as it relates to practices that maybe were not resulting in either transparent or predictable permitting processes, or were resulting in suboptimal kind of water quality outcomes. And we outlined them in this document we published about a year, well, I guess less than a year ago now, to guide not only some of the examination of what we would do, what regulators might want to take a look at, but also to shape some of the research that we were doing kind of midstream. And we had basically four categories as we defined them of all the different things that came up in terms of barriers in the existing practices that people were using, such as, which is fairly obvious and we've talked about already, not using existing standards that were not designed or tested for solar installations, but also things like recognizing differences between post-construction and construction permit goals in some of the jurisdictions we looked at that were resulting in some conflicts or some inconsistency on the way that and the kind of best practices on site that were being required. The difficulty on cross-jurisdictional interpretations, particularly across local jurisdictions, that was where we saw a big problem with administration of things like construction stormwater permits and other water quality, and even sometimes local water quality goals. And the lack of data-driven processes about some of the characteristics like Dr. Mulla had described on the layout of the site, which solar developers pretty much exclusively look at their array layout on the basis of whether or not panels are shading each other. And they have not really ever looked or incorporated standards that looked at the panel array as a means of mitigating for specific potential stormwater risks or water quality risks. Similarly, things like other site standards that were not scientifically driven that were being incorporated in an ad hoc manner. We did develop then a series of what we called our interim best practices, which is addressing each one of those four categories of barrier. And here's just a kind of some examples that we came up with using solar-specific best practices and standards. Example, looking to the final stabilization standards that are in, of course, the construction stormwater permits. That the incentive for developers is to vegetate the site as quickly as possible post-construction or at the end of construction, which is a disincentive to the use of the better ground cover in terms of what the study has said uh, um, over the long haul, kind of the post-construction period from when they leave the site until the site is decommissioned, that you would prefer to have a native or a pollinator or deep-rooted ground cover rather than the typical fast establishing. And the final stabilization standards, which are focused on the fast establishment, maybe are discouraging, or were definitely discouraging, because we had a lot of conversations with developers about this, the use of what would be, we would say, the better water quality outcome in terms of ground cover. We also encourage the, optimal or improve water quality outcomes, really looking at the model of identifying what the full water quality benefits are from the site. Typically, people look at just meeting the minimum standards, and what we discovered is that in a number of cases, there were practices being put in place for a variety of reasons that were actually resulting in exceeding the minimum standards and actually creating water quality amenities relative to the surrounding lands, and even potentially things that could benefit the rural watersheds that are agricultural based, and which of course don't have runoff standards associated with them. And then finally, kind of just the notion of creating cross-jurisdictional consistency, the opportunity that states have, and actually the EPA as well at the national level, in terms of providing training for local officials and creating of scientifically validated best practices. Here's just an example from the page that we have in that best practices. This is for permitting best practices directed at the authorities having jurisdiction to removing inadvertent barriers to the kind of co-benefit or multi-benefit ground covers. And an example that we pulled from the state of Indiana, where they actually, in their stormwater construction permit, had incorporated a standard that allowed some flexibility around final stabilization standards when native vegetation is being used as part of the BMPs. So, this is being done in a few places. Indiana actually did this not with an eye toward solar, but to just an eye toward encouraging green infrastructure approaches. But we thought it was very helpful, an example for them to look at and for other regulators to consider in terms of the solar standards. We also did develop these kind of interim best practices for solar projects, so not just the regulators, but what actual developers and site engineers and landscape architects should be doing in terms of understanding, practicing site design for disconnection, really looking for a green infrastructure approach, which not only creates co-benefits, but better water quality outcomes. Very important to use low impact development techniques, particularly in the construction process, because as Dr. Mulla noted, compaction is probably the primary barrier to the use of the disconnected site as a BMP for mitigating stormwater runoff and increasing infiltration, and really looking sometimes beyond the design storm in terms of whether or not you're creating an amenity that should be recognized in the regulatory process, and putting that in front of regulators. This is for the developer to do. We are going to be, these interim best practices, we're going to be doing some additional work on this and incorporating directly the findings of the final study that Dr. Mulla and his colleagues and Jake and the wonderful work that they've done, addressing things specifically like soil depth in the best practices, recognizing this as a critical element in the evaluation of a site, which is generally not done in the practice of evaluating stormwater impacts of solar development now, as well as kind of incorporating the explicitly recommendations about compaction and how that might be addressed either during construction or post-construction, and recognizing both that there is a compaction issue not only in the construction process and at the surface, but also at the deeper levels of soil, particularly when you have deeper soils that relate to some of the vegetation. The disconnection issue here, of course, is one that we'll talk about. It's of less importance, as it turns out, than maybe other standards, but it is a mitigation a technique, particularly when you have shallower soils, that could be used to increase the ability of the site to infiltrate water. And then the vegetation and ground cover issues, where things like panel height do make a difference in terms of the viability and the density and sustainability of the site vis-a-vis ground cover as a BMP, if you want to think about it that way, and also the getting to the compaction issue, where the deeper root structures of certain kinds of vegetative species and diversity of species actually increases, lowers bulk density and increases infiltration even when you have denser soils, at least as the literature has stated, and kind of taking these things into consideration in our best practices. Again, here's our project website, where this ultimately will be all put on the site when we get it done. And we are happy to take additional comments on any of our interim documents, which we'll be modifying in the near term, or any suggestions that you might have about how we might improve this, and especially as we get to kind of cross-jurisdictional issues on these things, where not only the state regulator but also local regulators need to be addressing this in a consistent manner, so that we're getting all the benefits we can, that communities are getting the co-benefits for hosting these sites that they should be, and developers are seeing transparent and predictable permitting processes. So I will stop there.
All right, is there any questions for Brian?
I did see one comment about tile drainage. That's a new one we haven't thought about. No, our model does not currently account for tile drainage. So that may be something we have to deal with.
Yeah, and I will say that tile drainage is something that's usually handled in the local permit process. Most counties, at least in the Midwest, are addressing tile drainage explicitly in their permit, in their land use permit, I should say, not necessarily in the construction stormwater permit, in terms of maintaining the existing drainage systems and protecting them, and making the developer and the project, liable for keeping those things in place. How that affects the stormwater, as Dr. Mulla said, I don't think we've addressed directly.
Well, I mean, one way that it could be done very simply is just to, take the initial results and try to do what is done basically in the hydrologic group classification, where you change the soil drainage class from a D to a B or something like that. We can think about maybe how to do that for the tighter soils.
And I believe we're over our allotted time now by a couple of minutes, but we're happy again to take additional questions. If you have things that occur to you that you didn't ask, feel free to contact me or Dr. Mulla directly. Either one of us will be happy to kind of answer these questions. And we would really look forward to whatever we can do kind of as we go into this project. For the next, I'll make the offer for the next 6 months. Most of our work is going to be around training and dissemination of these findings. And we are happy to go and talk to organizations and present these materials and the details here, so that we can have some, because our goal really in this whole project goal is to create that kind of transparent and predictable process around stormwater and solar development, and to enable deployment to happen in a way that is predictable for the industry, as well as for the making sure that co-benefits are flowing to host communities as these projects are developed.
Great, well, thank you. And if you wanted to share your email address, Brian, with those that are still with us, you could add that to the chat, and they could follow up with you later if they are interested. But just wanted to thank both of you again for joining us today and sharing your very interesting and important work with all of us. We really appreciate your time and learning from you. So thanks again for joining us.
Thanks, everybody.
Thank you.